Right, so we derived the statement of the conservation of momentum for objects that are colliding, and they also could be coalescing, that means sticking together, or a single object could be exploding into pieces. And conservation momentum says that in those kinds of collisions, the total initial momentum is equal to the total final momentum. As long as initial is just before the collision, final is just after the collision, we have a very quick collision. That means that the impulse approximation applies. So let's use that to try to answer the beginning of problem 1, first two parts of it. So we had a hockey puck colliding with a curling stone, and the hockey puck was moving in the x direction, curling stone at rest. The two stick together. They stick together and they're not just going to stop. They'll keep moving, but they'll move at a slower speed if you have some intuition about that. But in any case, we don't need to have any intuition. The question is, what's the velocity x component of the puck afterwards? So we're going to apply the statement of the conservation of momentum to this. And in this case, everything's moving along the plus x direction, or at least initially along the x direction. So let's apply the statement of the conservation of momentum for x components. Total initial x momentum is equal to the total final x momentum. Initially, the 3 kilogram puck is moving at 3 meters per second in the plus x direction. That's its x velocity component. So that's the total initial momentum x component for the puck. The stone initially has 0 x momentum because it's not moving at all. And then the total final momentum, we can sort of treat this as one combined object. It's going to be moving as a single object because they stuck together with that Velcro. And that means there's a single object of mass 15 kilograms, and it's moving with an unknown final velocity, Vx final. So the total momentum in the final state only has one term to it because there's only one object moving. They stuck together. And so if we use that to solve for Vx final, we get Vx final as 0.6 meters per second. So it's moving much slower than the puck was moving originally. Part B, suppose that what I said here about the Velcro wasn't true. The two do not stick together, but we make a measurement and we find out the 12 kilogram stone ends up moving at 1 meter per second in the plus x direction afterwards. Then what is the final velocity, magnitude, and direction of the 3 kilogram puck? We'll assume that friction imparts a negligible impulse, and therefore we can apply the conservation of momentum. And same process as before. Initially, nothing changes. We have the same initial x momentum for the puck and for the stone, but now the final state changes. We know the 12 kilogram stone ends up moving with a velocity x component of 1 meter per second plus 1. It's going along the plus x direction. And the 3 kilogram puck is moving with an unknown final velocity x component. So I call that V3x final to remind me that it goes with the 3 kilogram puck. And I can just solve for that in this equation, and we get V3x final is minus 1 meter per second. I know that's kind of short, but let's take a break, and we'll be back because the next section had a bit more.